In this presentation, I am going to explain the previous gate questions and answers and the topic power electronics and drives. This is a part 2. Part 1, I have already explained that one. Another presentation. Now let us see the problem 1. A three-phase current source inverter used for the speed control of an induction motor that is to be realized using the MOSFET switches as shown below. The switches S1 to S6 are identical switches. Therefore, this is the current source inverter switches S1 to S6, and of course this is a input inductor, and this is a induction motor, and the proper configuration for realizing the switch S1 to S6. For realizing the switch S1 to S6, what is the configuration? That is the question. Therefore, in this case, here you can say that one because of this is an inductive load, that is induction motor is an inductive load. In that case, you may require to have a negative voltage with a positive current like that. Even, I mean, in that case, only the switch configuration shown in the option C shows the bidirectional. The bidirectional power flow is required because of the inductive nature of the load. Therefore, in this case, the option C, if you see looking to that one, the current can have a positive current or it can have a negative current also. Therefore, that is in the case of induction motors, you may require with a positive voltage with a negative current. In that case, this type of switch can be opted. Therefore, in this case, other switches will not satisfy this bidirectional power flow. Therefore, the answer is option C. Coming to the problem 2, the circuit turn off time of an SCR is defined as the time, first one, taken by the SCR turn to be off. B, required for an SCR current to be become 0. C, for which the SCR is reverse biased by the commutation circuit, that duration. And D is for which the SCR is reverse biased to reduce its current below the holding current. Therefore, coming to that, once an SCR starts conducting by an forward current is conducting, the gate has no control on it and the device can be brought back to the blocking state only by reducing the forward current to a level below the holding current. And this process of turning mechanism, that's called the commutation, and this time is known as the circuit turn off time of an SCR. Therefore, in this case, the option D is the correct. It is for which the SCR is reverse biased to reduce the current below the holding value of the current. Now coming to the problem 3, a voltage commutator chopper circuit operated at 500 Hz is shown here. This is a voltage commutator chopper circuit. And if the maximum value of the load current is, maximum value of this current is 10 amperes, then the maximum current through the main SCR and auxiliary SCR. This is the main SCR and this is the auxiliary SCR. That's the question. Now coming to the circuit of diagram of this one, here assume that just before switching on this one, here already this capacitor has been charged with a plus polarity at the top and minus polarity at the bottom. That's to the same value of this input voltage. I'm putting this as Vs. For plus to minus Vs, it's already charged before turning on the SCR. Now, when it is turned on here, plus here and minus here, when it is turned on here, now this is the current flowing through this one, load current is carried by this main SCR. Same time, there's another path like this one through this diode, inductor and capacitor. Therefore, in that case, the capacitor will be discharging and I come to 0 voltage and that will be charging in the reverse direction with the plus and minus Vs. That process is happening. Therefore, here during that period, if you see that one, the current through the main SCR is equal to the load current plus the current that is charging the capacitor. Of the capacitor charging current, that circuit is this one that consists of inductor and capacitance, and that based on that one, that resonance circuit as such L and C, and the resonant frequency of this circuit that is given by 1 by root of LC, and we have given the L value and C value, and similarly the peak value of this current, that is the peak, this is a ringing circuit in which the peak value of the current through this circuit ICP can be calculated, that is equal to whatever this voltage Vs divided by omega naught into L, where omega naught is equal to the resonant frequency 1 by root of LC. Therefore, substituting that one, we will be getting corresponding to C and L, it will be getting 2 amperes. Therefore, 2 ampere is the maximum or peak value of this capacitor current. Therefore, in this case, the capacitor is discharging and then it is charging the opposite direction with the plus and minus here and within this time. Therefore, the peak value of that current is equal to ICP, which is equal to 2 amperes. And once, in order to turn off this SCR, the method is that this already it is charged with a plus here and minus here. We'll be turning on the auxiliary SCR. Then the reverse voltage will be coming onto the main SCR. Then that gets turned off. That is why it is called a voltage commutated chopper. In that case, after that one, the load current will be carried by this circuit, capacitor and auxiliary SCR, and through this load, and that is coming back this one. Therefore, in that case, the capacitor is charging with a constant load current, and the path is like this one. Therefore, the current through the auxiliary SCR is same as this load current, and the maximum current through this that main SCR is given by the load current plus what is the maximum current of this capacitor, that is this ICP. Therefore, the maximum current through the main SCR, that's equal to the load current. When this is conducting, it carries the load current plus the charging of this capacitor. Therefore, ICP, which is equal to 2 amperes, 12 amperes. And the maximum current through this auxiliary thyristor, that is once it is turned off, this has the load current is to be carried by this auxiliary thyristor. Therefore that is equal to the load current 10 amperes. Therefore 12 amperes is the maximum current through the main SCR, and auxiliary SCR maximum current equal to 10 amperes. The option A is the correct. Therefore answer is option A. Now let us see the problem 4, in which a solar energy installation utilizes a three-phase bridge converter, this one, to feed energy into power system through a transformer for 400 volts per 400 volts, this one, is shown below. And the energy is collected in a bank of 400 volt battery, and it's connected to a converter through a large filter choke of the resistance 10 ohms. So this is the circuit diagram. Question is that the maximum current through the battery will be, what is the maximum current through the battery? In order to find out that one, let us see this is a three-phase converter. The average output voltage of a three-phase bridge converter basic equation is that 3 VML by pi cos alpha. 3 maximum value of the line voltage divided by pi into cos alpha, where alpha is the firing angle of this converter. Now the maximum magnitude output voltage gets when alpha equal to 0. Therefore, the maximum value of the output voltage can be obtained by 3 VML by pi, or 3 into maximum value of the line voltage equal to root 2 times 400 RMS value. 3 into root 2 into 400 divided by pi, which is equal to 540.19 volts. That is the maximum value of the output voltage. Now for the battery voltage is equal to 400 volts. Now applying the Kirchhoff's voltage law to this loop, has said this one. This voltage equal to, that is 540.19 voltage equal to the battery voltage plus the average voltage across the inductor equals 0, because as per the volt second balance concept, average voltage across the inductor equals 0. Therefore, the remaining, that is this voltage equal to the battery voltage plus the current into this resistance, that is current into 10 ohms. Therefore, the average voltage across the inductor equals 0. That is why applying Kirchhoff's voltage law, we will be getting the maximum value of the output voltage equal to E plus I into this choke resistance, which is equal to 540.19 equal to 400 into 400 plus I into 10, or from that one, the current is equal to 14 amperes. Therefore, that current 14 amperes. In this case, the option A is the correct. That is, answer is option A. Continuing the same problem, that is here problem 5, same as the problem 4. A solar energy installation utilizes a three-phase bridge converter to feed energy into a power system through a transformer 400 volts per 400 volts, as shown in figure. The energy is collected to a bank of 400 volts battery and is connected to a converter through a large filter inductor of 10 ohms. The question is here, what is the kVA rating of the input transformer? What is the kVA rating of the input transformer? Therefore, here if you see the current, input current of this one, because this is a three-phase converter, the input current is, since the load current is a constant here, the current waveform at this point, you can say that one, we can say is a rectangular waveform in which that is changing from 30 degrees to 150 degree. Therefore, this is the shape of the current at this one. In order to calculate the voltage rating of the transformer or kVA rating of the transformer, we have to find out what is the fundamental magnitude, or we can say RMS value of the fundamental one, because this involves the harmonics. and this is having a half-hour symmetry. Ft equal to minus, it is equal to minus ft plus t by 2. Therefore, half-hour symmetry is there. Therefore, if you do the Fourier analysis, the Fourier constant a0 will be 0, but an and bn will be there. Then an is given at this equation 4 by pi into alpha plus 30 plus alpha plus 150 I0 cos omega t. But in this case, alpha equal to alpha, we can say that alpha equal to 0. Of course, that is then the bn is also given in this equation. Once you, from the an and bn, you can calculate what is a1. If you put here a1, you can calculate, it is equal to, instead of n you calculate 1, then we'll be getting 2 root 3 divided by pi into I naught sine alpha. B1 equal to 2 root 3 I naught by pi into cos alpha, for corresponding to firing angle alpha as such. Therefore, here, once you get what is the Fourier constant A as well as A1 and B1, then that is corresponding to the fundamental. The maximum value of the fundamental is given by square root of A1 square plus B1 square, root of A1 square plus B1 square. Now, the RMS value of the fundamental is given by root of A1 square plus B1 square divided by root 2. Therefore, we are taking root of this one and divide by root 2, or that will be getting root 6 divided by I naught by pi. Root 6 I naught divided by pi. I naught already we have I naught is equal to, here already in the previous problem it is calculated as 14 amperes. Substituting that here also 14 amperes, therefore it is equal to 0.78 into 14, which is equal to 10.92 amperes. Therefore, the RMS value of the fundamental, the current at this point is equal to 9. Of course, it is equal to 10.92 amperes. It is equal to 0.78 into 14. 10.92 amperes is the RMS value of the fundamental current, and the voltage rating, of course, that 400 volts. Therefore, the kVA rating is given by root 3 into VL into the RMS value of the fundamental, which will be getting root 3 into 400 into 10.92, which is equal to 7.5 kVA. Therefore, the answer option D is the answer. Here 7.5 kVA is the rating of the transformer, because the current is not a sinusoidal, it's a rectangle like this one. Therefore, it involves fundamental plus harmonics. What we have to calculate to rating of the kVA, we have to take the fundamental of the one, that is RMS value of the fundamental, that is multiplied with the voltage, and of course integrate the three phase, it is equal to root 3 VL into I, which is I1 fundamental RMS value, which is equal to 7.5 kVA. Option D is the answer. Now, coming to problem 6, the power electronics converter shown in the figure has a single pole double throw switch, single pole switch, and the pole P of the switch is connected alternately to point A and B. The converter, therefore, this can be either connected to the point A or it can be point B. Or when it is connected point A, then a source is coming in series resistance and this one. And when it is connected to B, it is a zero voltage. And this topology is similar to a buck converter or step down, like it is a step down chopper or a buck converter. And in that case, we can see that when it is connected, the voltage you'll be getting the whatever the supply voltage V in, and when it is connected to this B point, you'll be getting 0. Or the output voltage, normally it is the average value of the output voltage, and that is given by V0 by VD will be equal to T on divided by Ts, or V output voltage is equal to D times the input voltage. That is the step down chopper output voltage, average output voltage equal to duty ratio times the input voltage, where duty ratio, duty cycle both same, that is equal to the on period divided by the total time period. Therefore, this is the on period and this total time period. That ratio we call it as duty ratio. Therefore, this circuit is similar to the step down chopper or buck converter. Therefore, the answer is option A. Now, coming to the problem 7, figure shows a composite switch consists of power BJT in series with a diode. That this one, a power BJT in series with a diode. Assuming that transistor switch and the diodes are ideal, what is the IV characteristic of the composite? What is the ID characteristic of this one? IV characteristic of this one. As you know that when here diode is connected this one, that indicates that it can have only positive current. That is the first thing. But that is why it can have only the positive current. That is, this is like it cannot have a negative current. All these have negative. It can only the positive current. And in this case, when there is zero, that is when there is a zero current, that is it's not conducting zero current, the voltage across this one can be either plus or minus. The voltage across the switch can be either plus or minus. Or in that case, we can say that one the voltage across that one can be either positive or negative. And when it is conducting, it can have only the positive current. Therefore, the characteristics corresponding to this BJT with a diode like this one is the option C. Therefore, answer is option C. And since diode is connected in series with BJT, the current I can never be a negative. It can never be negative. When a current flows, the voltage across which is zero. And when the current is zero, the voltage can be either positive or negative. Either positive or negative. When it is when the voltage across can be when the current is zero as such. When the voltage across is when voltage across the switch is zero, and when current is zero, the voltage can be either positive or negative. Therefore, the answer is option C. Now let us see problem 8. The fully controlled thyristor converter in the figure is fed from a single phase source. When the firing angle is 0 degree, the DC output voltage the converter is 300 volts. What will be the output voltage for a firing angle 60 degree, assuming the continuous conduction? Now this is the single phase thyristor converter, same thing here. And during the positive hour cycle, it is fired with an angle firing angle alpha, and that until the next pi plus alpha, that is conducting. Then output voltage waveform is like this one. This is the input voltage and this is output voltage, and the average output voltage can be found out 1 by pi integral alpha to pi plus alpha Vm sin omega t, and if you integrate it, I am getting it is equal to 2 Vm by pi cos alpha. Therefore, the average value of this output voltage equal to 2 Vm by pi cos alpha for a single phase fully controlled thyristor converter. Now coming to the question here, when firing angle equals 0, the DC output voltage equal to 300 volts. That is, when alpha equal to 0 or when cos alpha equal to unity, VDC equal to 2 Vm by pi cos alpha. Or when alpha equal to 0, VDC equal to 2 Vm by pi cos alpha, which is equal to 300 volts. Now, question is that when firing angle equal to 60 degree, what is the average output voltage? Or it is assuming that what is the output voltage corresponding to 60 degree. Therefore, 60 degree corresponding to that one, VDC equal to 2 Vm by pi cos 60. Already 2 Vm by pi equal to 300. Therefore, 300 into cos 60 equal to 1 by 2. It is equal to 150 volts. Therefore, the 150 volt means the answer is, of course, A. Therefore, the answer is option A. When corresponding to firing angle 60, the output voltage of the converter equal to 150 volt. That is option A. Now let us see the problem 9. So the current source inverter shown in the figure is operated by alternatively turning on the thyristor pairs T1 and T2. This is T1 and T2, and T3 and T4. T3 and T4. If the load is purely resistive, the load what we are considering is a purely resistive, the theoretical maximum output frequency obtained by this one. What is the theoretical maximum output frequency obtained by a current source inverter? And let us see that one. Of course, that is before T3 and T4 already conducting. That is, before turning on T1 and T2, assume that T3 and T4 are already conducting. Or when T3 and T4 are already conducting, the path is like that. Constant current is coming for T3 through this capacitor, through this diode, through this slot, through this diode. It is through this capacitor, through this SCR, it is T3. Therefore, that is the path of the current. And in that case, the capacitor will be charged with a plus polarity and minus polarity. And this capacitor will be charged with a plus polarity and minus polarity. For whenever we want to commute the devices T3 and T4, we will be switching on T1. When we are switching on T1, here plus and minus voltage, therefore that negative voltage comes here, and that get the voltage commutation happens for the T0. Here T1, here T3 it is getting turned off. Similarly, here also, since the voltage plus and minus here, when this is of course this is turned on, here a minus voltage comes here, or this is also getting turned off. Therefore, after that one, the path is like that one. The constant current is flowing from T1 and through this capacitor charging in the opposite direction with the plus and minus here, and through this diode, and through this lot, again through this diode, and capacitor with the plus and minus charging, and returning back to T2 and is coming back that one. In that case, the capacitor voltage will become charging to plus here and minus here. Similarly, it will plus here and minus here. Then that will be repeating. Whenever you want to switch off this one, again you switch on the T3 and T4. Therefore, this is the way in which it is working. Therefore, in the path we can see that there are two capacitors, C1 and C2, or can say that one, and one resistor is also there. Therefore, that is shown here as such. Therefore, let even T3 and T4 are already conduction time taken. The triggering of T1 and T2 and T3 and T4 are force commutated. And again at T equal to T by 2, of course T1 and T2 are force commutated. This circuit will be repeating. Therefore, in this circuit, this path, no, capacitor, resistor, and capacitor. This is that is caused because of the capacitor charging that is getting commutated. Therefore, this path, if you consider, what is the time constant of that one? That is total capacity will become 0.1 plus, sorry, 0.1 and 0.1 in series. Therefore, it is equal to 0.05 and this is equal to 10 ohm. 0.05 microfarad and 10 ohm is the resistance and capacitance as such. Capacitance and resistance. And the time constant of the circuit is tau is given by 10 into 0.05. Of course, microsecond. That comes 0. Microseconds is the time constant. And in a one cycle, or that is the total time period of in one cycle, there are such 4 time constant happens, or the 4 tau, which is equal to 4 into 0.5 microsecond. 2 microsecond is the, therefore, this is the minimum time required. This is the minimum time required means that the maximum output frequency can be 1 by this minimum time, that is 1 by 2 microsecond, which is equal to 500 kilohertz. The maximum frequency that can be obtained with this current source inverter can be calculated as 4 times tau, which is equal to 4 times into 0.5, which is equal to 2 microsecond, or maximum frequency equal to 1 by 2 microsecond, which is equal to 500 kilohertz. 500 kilohertz, the answer is C. Answer is option C. For that much frequency, it can be operated, this current source inverter. Now let us see the problem 10. Therefore, in the chopper circuit shown, the main thyristor Tm is operated at a duty ratio of 0.8, which is much larger than the commutation interval. If the maximum allowable reapplied dV by dt of this one is equal to 50 volts per microsecond, what should be the theoretical minimum value of this C1? That is, assume that ripple current through inductor, that is negligible. That ripple current is negligible. Therefore, this is a circuit as chopper circuit. In this case, this is the main SCR, and the main SCR, the maximum dV by dt permitted is 50 volts per microseconds, and the current ripple is negligible also. And here the load current can be calculated. Load current is equal to 100 divided by 8. That is the, it is equal to 100 divided by 8 is the load current, and the current through Tm. The current through Tm that is calculated as Im, that can be calculated as the duty ratio into the whatever this 12.5. That is, duty ratio means 0.8 into 12.5, 10 amperes. Therefore, the current through the main thyristor Tm is equal to, we'll be calculating as 10 amperes. And this one, therefore, the maximum permitted dV by dt equal to 50 volt per microsecond. Or relating that one, the Im, that Im can be related to that one. Im equal to this path as such here. It is equal to C dV by dt, where C into dV by dt equal to 50 volts per microsecond. That is equal to Im or 10 amperes. From that one, C you can be calculated or 10 divided by 50 volt per microsecond, or 0.2 microfarad is the value of the capacitors required. Therefore, this capacitance required value is equal to 0.2 microfarad. The answer is the option A. Now let us see problem 11 as match the switch arrangements on the top row to the steady state VI characteristics on the lower row. The steady state operating points are shown by large black dots. The switches are, a diode is there, and a CR is there, IGBT is there, and IGBT with a feedback diodes is there. The 4 switches are there. Say uncontrolled switch, this is a semi-controlled switch, this is a controlled switch as a controlled switch with a freewheeling, feedback diode. You can say the feedback diode as such. But these are the 4 switches, and the VI characteristics shown, we have to match it that one. For example, in this case, if you say the answer, you can say that C is the, we'll see one by one. In the case of C here, you can say that one, this is a diode as such. The diode to which is to be matched. Because diode means if there is, for example, if the current is positive here, you will be getting the voltage equal to 0. The corresponding to voltage 0, the current can be only positive current. It cannot drive the negative current. Similarly, the voltage can be either, we can say that one here, that is one. Similarly, when current equals 0, it can have a negative voltage, peak inverse voltage. Therefore, this is when current voltage equals 0, current is positive. When current equals 0, voltage is negative. Therefore, this is the VA characteristic corresponding to the diode. Therefore, that P is corresponding, it is equal to 4 as such. Second Q, this is an SCR. Here also we can see that one, it is equal to, you can have only the positive direction of current. You cannot have a negative. Therefore, this is the thing. But the voltage can be either, when current equals 0, the voltage can be either positive or negative. Therefore, that is the corresponding to the SCR characteristic. Therefore, the Q is corresponding to the option 3. And next one here, it is a IGBT as such. IGBT here, we can say that IGBT here, it can have only one direction, that is positive, and similarly the voltage also can have one direction. So this is corresponding to an IGBT. But if you are introducing a feedback diode like this one, you can have a positive current as well as a negative current. Therefore, this will be changing to when you are introducing a feedback, that will be changing to here, it is changing to this one. Therefore, it can have either positive current or a negative current, but voltage always positive. Or this corresponding to the IGBT with a feedback diodes. Therefore, that one, that is S is corresponding to, it is equal to 2. Therefore, the option is option C, P4 Q3 R1 S2. Therefore, answer is option C.